Good afternoon, everyone. My name is Patrick. I'm Silke's postdoc here at the University of Nottingham, and our speaker today is Professor David Kaiser from MIT. So he's a professor of physics and a professor of history of science at MIT. David is actually an author of many books, which are between physics and history of science. Also, many articles. He's been featured in New York Times, the New Yorker magazine, Nature, Science, Scientific American, the Huffington Post, and the London Review of Books. And also he appeared on the National Public Radio, BBC Radio, and Nova television programs. He's also a fellow of the American Physical Society, and he's awarded with several prizes, including the Kaiser Prize, the Laureate Award, the Frank E. Perkins Award, and he's also a Mac Vicker faculty fellow. So today, David is going to discuss non-perturbative dynamics of post-inflation reheating. And with that, I would like to give him the stage. So David, please.
Terrific. Well, thank you so much. I'm really delighted to be able to talk with you today. I'm looking forward to our discussion. So as you just heard, I'm going to talk about some work on the phase that we think likely occurred just after the very early universe phase of cosmic inflation, this post-inflation reheating era. And so I'm going to be talking about a body of work I've really been very lucky to work on with a series of wonderful collaborators, stretching back now over the past decade or so. And so I'll focus on this review article that I really enjoyed working on with Mustafa, Mark, and Joanna. The review article itself is now just about 10 years old. Mustafa, Mark, and Joanna were all postdocs at MIT when we worked on this together some years ago. Working on the review article actually helped inspire a new series of work that unfolded in kind of two parts. So a trio of papers with these colleagues here, Matt, Ani, Chanda, and Evangelos. And those were, as you'll see, kind of semi-analytic. So they were focusing on the early phase of the reheating epoch. And then building on that, Evangelos with a new set of colleagues, Yorinda, Rachel, and Tom Giblin, we were able to push into full-scale lattice simulations to explore some of the more rich nonlinear effects toward the later stages of reheating. And so I'm going to focus on this work. I want to be careful, though, and say right at the beginning, there's some marvelous, more recent reviews. I'm sure the topic is of broader interest, especially for the group with whom I'm joining today. So whereas I still think there's plenty of reasons to go back to this 10-year-old review article that Mustafa, Mark, Joanna, and I had written, there really is some marvelous, even much more recent review work in the literature as well by these colleagues. So I want to point those out before I forget. And also what I want to emphasize is when I got this really lovely invitation to talk with your group, it made me go back to some of this work that my own colleagues and I had been pursuing and to think about what are points of contact that might be fun to explore with the kinds of actual real experiments, benchtop and analog gravity experiments that many people who I think are probably joining right now have been so deeply involved with. So I'm going to try to highlight some aspects from the body of work that I've had fun working on with these colleagues, and then kind of give pointers to where I think there might be interesting things to think about, where there might be room for really constructive dialogue between these new generation experiments and some of this analytic, semi-analytic, and numerical lattice simulation work. That's what I want to share with you today. And again, I look forward to our discussions. So the talk has three main parts. I want to just remind you, it's probably familiar, but I'll remind you some of the reasons why cosmologists continue to be interested in this epoch, in trying to understand this post-inflation reheating phase. And then I'll talk about these two main kind of early and late phases that I have come to think about when thinking about reheating, this early resonant energy transfer with lots of collective phenomena and really I think very cool and very pretty physics. And then some of these distinct processes that really only come to bear when we get more deeply into the fully nonlinear regime. So I think when I think about the status of early universe cosmology today, I think it's really a tale of two epochs. We have a remarkable framework, a very a sort of analytic framework that's now been studied with care for more than 40 years, with which to try to understand some of the earliest moments in cosmic history, this era of cosmic inflation. And as you know, that does many things on the kind of large scale structure of the universe. It should yield a universe that is spatially flat, that is homogeneous to a high degree, and so on. It also should seed what will grow into large-scale structure. It should provide a well-based physical mechanism that will lead to things like the formation of galaxies, clusters, galaxies, and all the rest. And then the next epoch, as we kind of play the tape forward, as we think about moving the clock forward in cosmic history, the next time or set of phenomena for which we have a comparable analytic and empirical real kind of dialogue is actually Big Bang nucleosynthesis. Lots of important things must have happened between these epochs, and yet the next time in cosmic history, when we have such a clear dialogue, constructed dialogue between really constraining empirical data, real measurements that can say it's like this but not like that. That really comes all the way at Big Bang nucleosynthesis, and as you likely know, these two epochs are separated by an enormous gulf in either whether we consider energy scales for typical processes involved or the time scales over which they unfold. So we have these two really remarkable eras that are now subject to a kind of empirical constraint and constructive dialogue, but there's a lot that seems to have had to happen in between. So here's a quick cartoon version of how I've come to think about cosmic inflation. Many of us do these days. So there could be some very interesting, in fact, highly nonlinear physics that might have triggered the onset of inflation. And we can actually talk about some of that as well if folks are interested. But then fairly generically, it seems, the universe likely settled into a phase of what we call slow roll, where the expansion of space-time itself was quite smooth. It was being driven by one or more fields that behaved as if they were scalar fields. They might indeed have just been simply scalar fields. Those fields were evolving rather slowly in a kind of gentle potential, undergoing what we call slow roll. During that time, the kinetic energy of the fields was rather tiny compared to the potential energy. The change in the rate of stretching of space itself was small, so space was stretching nearly like a de Sitter phase. It's during this epoch, again, as I'm sure you know, when there are quantum fluctuations of this one or more fields that are driving inflation. Those fluctuations get amplified and stretched. And thank goodness, these are such tiny fluctuations in this era that we can get by with really accurate calculations, even though we're still in a linearized analysis. And then sometime later, inflation has to end. And that's the period I'll be talking about for today. We typically understand it ending as when this field, or the fields that are driving inflation, reach the global minimum of their potential, and they typically begin oscillating quite rapidly around the minimum. And that's when things like the energy that was locked up in the inflaton field or fields gets dispersed into other forms of matter. There can be very, very distinct types of physical processes that are very different from this slow roll era during the main parts of inflation. So the physics after inflation, including this post-inflation reheating phase, generically involves non-perturbative and indeed deeply nonlinear dynamics. So why should we study reheating? I think there are a couple of good motivations. One is this kind of two epochs motivation I've shared already earlier. Also, I think reheating offers a pretty rare opportunity. If one is thinking more from a kind of high energy theory point of view, this is a phase within which we can try to understand well-motivated models of high energy physics that otherwise are very difficult to probe empirically, explore a wide range of interactions, maybe start identifying plausible dark matter candidates, maybe account for things like matter antimatter asymmetry. There's a lot that had to happen under really quite exotic conditions, very high temperatures, very high densities. And here is a phase with which to try to explore those kinds of possible interactions. If you're anchored more in a kind of empirical astrophysics or cosmology point of view, we still have to pay attention to reheating. And here, one of the most important to my mind is to really try to preserve this remarkable fit that we have between predictions from various models or families of models of inflation and these high precision measurements of things like the anisotropies in the cosmic microwave background radiation. So, which is to say more generally, we need to really understand the expansion history of the universe because we rely on that to make these maps between predictions of extraordinarily early and very high energy phenomena, like during inflation, and phenomena that are now measured to better than percent level accuracy in things like the CMB. So we have to understand how the scale factor A was evolving so we can really connect physical length scales with co-moving length scales, to put it a bit more prosaically. Here's a quick picture of that. This comes from actually my friend Mustafa Amin. I find this very helpful. So on the vertical axis, I'm plotting the physical value of the Hubble radius. And on the horizontal, I'm plotting time, now measured, say, in e-folds of expansion, the log of that scale factor. So during inflation, the Hubble radius is nearly constant. And then we have some transition. If there's a very fast transition, if reheating is extremely efficient, then the universe should transition to a radiation-dominated equation of state relatively quickly. Then we know the rate at which the Hubble radius will grow during that phase. And then at some later time, we might become cosmological constant dominated. The point is, if we're following the evolution of some perturbations on some characteristic length scale lambda, the physical length scale, of course, is changing with the scale factor. So perturbations that start out much smaller than the Hubble radius during inflation will cross outside the Hubble radius before inflation ends, and they'll cross back inside the Hubble radius. The ones that we are interested in are those that cross back inside the Hubble radius just as the photons are beginning to decouple from this hot plasma around the time of recombination. And so that's how we begin to make a map between the perturbations that are laid down or visible in the CMB and the dynamics that happened much, much, much earlier during inflation. Well, you see that map depends on what happens in between, on how the Hubble radius itself is evolving during these distinct epochs. If instead of a very efficient phase of reheating, there was some delay, there could have been some intermediate period. Maybe the universe expanded for some finite duration of time, not as radiation, but maybe as matter-dominated or some other equation of state. Then we're going to start changing how we map the phenomena that can now be measured by things like the Planck satellite and many other CMB experiments, and how we infer the physics that must have been happening when those perturbations were being amplified and excited during inflation. And so this gets built in now to even our precision cosmology, what we call n star, the number of E-folds before the end of inflation, when the CMB relevant perturbations first crossed outside Hubble radius. This would be n star in scenario 1. This is n star in scenario 2. That actually depends on this reheating history. So it depends on a lot of stuff that happened during inflation. We can answer that if we have a model of inflation. We can answer these. These are not independent inputs. But it also depends on what happened during this immediate post-inflation era. Basically, how quickly did the universe come to a radiation-dominated equation of state? And that should get all of us really excited and or nervous, because these high precision measurements of things like the spectral index for these CMB perturbations, they tend to depend linearly or inversely with the inferred value of n star, of when the CMB pivot scale first exited the Hubble radius. So if we're going to try to get better and more accuracy on things like the CMB observables, then we're going to soon be kind of reheating limited, because there's residual uncertainty on this last part of the story of how we relate perturbations here to here. That's one reason, among many others, but one why I think we really why this post-inflation reheating epoch really deserves continued and very close study. There are other reasons, and this is related to the one I was just saying. My very dear friend and mentor, Alan Guth, likes to say that inflation had to put the bang in the Big Bang. And I offer a friendly amendment to Alan's lovely catchphrase. It's actually reheating that's going to launch the Big Bang as we have come to know it. Inflation is absolutely critical to this story, but it's reheating that has to set the conditions from which the standard Big Bang evolution would then follow. And there are at least three that we can think about. The first, as I just mentioned in the previous slide, one thing that has to happen after inflation is that the hot plasma has to come into a radiation-dominated equation of state. I have a little picture of a Crookes radiometer to remind us that radiation actually has pressure as well as energy density, that we really need to have a particular kind of equation of state for that fluid, and that's very different from the equation of state during inflation, at least typically. A second thing has to happen, and that's that the energy that was locked within this fundamental scalar field, or whatever matter was driving inflation, that has to get dispersed from that form of matter and has to start populating all the other stuff that's going to make up us and make up galaxies and maybe even make dark matter as well. We must, at the very least, produce a hot bath of standard model particles. They had to come from somewhere. And they seem to have played a very unimportant role, at least typically, during inflation. So reheating, again, is an era when we better populate the universe with stuff that we know about and of which we're made. And finally, that stuff has to come into thermal equilibrium. It doesn't just have to have a radiation equation of state. It really should become a black body. It should become, the equation of state should, the matter should achieve an equilibrium state at some high temperature, reheating temperature. And the remarkable thing is that these three ingredients don't have to happen at the same time. They can depend on quite different types of physical processes that might have very different kind of inherent timescales. And again, that's something that we want to keep in mind as we come to study this immediate post-inflation reheating phase. Let me talk about the first phase then, the earliest phase of how we now have come to understand the reheating. So soon after the end of inflation, this phase of very resonant energy transfer. The original idea, really starting months after the first models of inflation had themselves been written down, was to consider single body decays. This was being done by extremely talented, at least one now Nobel laureate, scholars in high energy particle theory. And they did what particle theorists do best. They tried to study kind of particle interactions by studying Feynman diagrams and calculating decay rates and so on. So if you put in as a simple toy model that the inflaton particle I'll call phi could couple to, say, pairs of particles, these could be scalars or fermions or whatever you'd like, then at tree or at lowest order, we can calculate the decay rate. It's going to depend on things like the coupling constant, the mass of the inflaton, and so on. We also separately know how the Hubble parameter is expanding after the end of inflation. If we have this kind of hot bath in thermal equilibrium, then the energy density can expand like T to the fourth, T being the temperature. And the earliest papers basically said, let's consider when these two rates become comparable and say that's what the reheat temperature will be. We're going to estimate the reheat temperature from this phase by considering when the single body decay rate is comparable to the rate at which space is stretching. And that gives you a pretty good estimate, or a very straightforward estimate, for what the reheat temperature should be. And you can see it can be it can be large in astrophysical scales. It's growing, scaling like the square root of the Planck mass. It can be very high, and depends then on the decay rate and so on. Okay, so I like to think of this as kind of trickle-down reheating. This is a kind of every inflaton for itself. Maybe that makes sense for the early 80s, thinking about economic theory. Anyway, I won't push the metaphor too hard. This is basically single body decay studied by Feynman diagrams. It's an interesting first estimate, but it turned out to have been really, I think, quite insufficient or inadequate. So about a dozen years later, there was a huge flurry of activity starting really in the mid-1990s, led by people like Lev Kaufman, Andrei Linde, and Alexei Starobinski, with many other people contributing. Robert Brandenburger had some very important work and so on. But a real kind of new phase in our understanding of these early processes. And this is really, instead of the kind of trickle-down economics picture, I think of this as the kind of Occupy Wall Street phase, where you have to think about extremely large, exponentially large occupation numbers, because you can have all these non-perturbative resonant effects. Instead of thinking about single inflatons decaying independently of each other, there can actually be coherent processes that can very rapidly transfer energy from that condensate of inflaton particles into decay products. So again, I'm going to thinking about this period here where the inflaton is oscillating rapidly around the minimum of its potential. And we can study things like this Mukhanov-Sasaki variable. This is a really convenient parameter, might be very familiar to you. This is a linear combination of the field fluctuations and one of the metric perturbations. This is the curvature on equal time hypersurfaces, we can think of that. This particular combination is gauge invariant, at least to linear order in perturbations. And remarkably, as Mukhanov and Sasaki independently each showed many years ago, we can write down the exact equation of motion for this gauge invariant combination. And it looks actually pretty straightforward. This is just linearizing the full field equations, but working in terms of a very kind of convenient set of parameters or of variables. What I want to focus on is this time-dependent effective frequency. This is not a simple harmonic oscillator. The frequency here can have all kinds of very important, very interesting structure to it. Again, that's, I'm sure, on many of your minds experimentally, and that's what I'm going to spend most of my time talking about today as well. So the frequency depends, of course, on the physical momentum and on the effective mass. And the effective mass has different types of contributions, and I'll unpack each of those in the next few slides. The main thing to think about now is just to keep in mind that each one of these contributions to the effective mass, and therefore to the effective frequency, they're time dependent. They depend on both the condensate phi and the time derivative phi dot. And so as phi is oscillating rapidly, these terms in the effective mass will oscillate as well. And that can drive all these very powerful resonance phenomena. So this brings us to some beautiful pure mathematics that was first figured out in the 1880s. This goes way back by people like Floquet. And so if we just consider an oscillator equation of that form, I'm going to write it a little more abstractly now. We have a second order differential equation for some quantity Q. In this case, these are Fourier modes. And we have some periodic function. This is where that periodic effective mass or effective frequency term would show up. Then generically, the solutions, exact solutions to this differential equation here, can be written in this very simple form, which is a triumph of 19th century applied mathematics. These functions P1 and P2 are both themselves periodic, with a period that's proportional to the period of this function f. So that's well known. They're basically just essentially sines and cosines at the lowest order. But you see these terms here. Whenever these coefficients mu have some non-zero real part, then you have these exponential instabilities in the solutions. You can have very, very rapid growth of these perturbations. The form of those exponents, their behavior, depends quite sensitively on the model you consider. So generically, there will exist some regions where mu is real for some wave number k, and some regions where it's not. So you have bands of rapid amplification, bands in, say, wave number space. But the behavior of those and how they vary with couplings and so on becomes highly, highly model dependent. And my colleagues and I wrote this out really quite, I think, in a hopefully pedagogically helpful way in that review article from about 10 years ago. The upshot is that this phenomena persists. These robust resonances will survive even in a self-consistently expanding universe, as long as the real part of these exponents is large on a scale set by the Hubble parameter. So there really exists this sort of explosive transfer of energies, even in an expanding universe, not only in, say, flat space. And that was figured out again, really throughout the mid and late 1990s. So if we can think about this at a kind of quantum field theory point of view as being the rapid production of particles in certain bins, certain modes k, when this adiabatic parameter departs strongly from 1. So we want to consider the rate at which the effective frequency itself is changing rapidly. It's during those periods where you tend to see these bursts of particle production. It's not a continuous production. It can be actually quite stochastic. These plots are actually taken from this very important, still landmark article by Kaufman, Linde, and Starobinsky, tons and tons of studies ever since, where you can see the growth of, say, an individual mode. The amplitude is growing in fits and starts, and you can see it's eventually, you see this exponential instability as you kind of coarse grain. The envelope is growing by that exponent mu. And as you count, say, the occupation number per mode, again, you'll see these enormous leaps, although it's not monotonic. Very soon after those first resonances were identified, many other scholars studied this for more complicated or higher spin systems. You find a comparable effect for decay into fermions. Now, of course, because of the exclusion principle, you don't get an exponential occupation number for fermions, but you certainly get a highly non-thermal distribution, as people like Patrick Green and Lev Kaufman showed in early 2000, and much more follow-up work since then. Others have studied the decay into spin 1 particles. These could be photons, they could be gluons, they could be more exotic gauge particles, spin 1 particles. Again, you see all kinds of effects that can be studied in a model-dependent way. And the work that I'll focus on with my own colleagues is looking at multiple scalar field models, where they have some features that I think are worthwhile to consider when we try to do realistic modeling of these very high energy phenomena. And once again, we see these characteristic resonances and transfers as well. Let me say a few words about the family of models that I've been focusing on with my colleagues and why I think this is a useful playground for exploring reheating more generally. So most models of high energy physics include more than one scalar degree of freedom at high energies. In fact, that's true even of our beloved standard model. At high energies, the Higgs sector actually has 4 interacting scalar degrees of freedom. In renormalizable gauges, the Goldstone modes remain in the spectrum. So even the standard model is already a multiscalar theory when we consider very high energies as appropriate, for, say, for an inflationary epoch. And then any effort, at least to date, to go beyond the standard model tends to introduce not a few, but many, many additional scalar degrees of freedom. All these SUSY partners, more exotic things. There could be gajillions of axions running around. So in general, my colleagues and I have considered a well-motivated ingredient to be multi-scalar fields to start with. That's not to the exclusion of fermions and gauge bosons. Let's at least get a bunch of interacting scalar fields in the mix. That's ingredient 1. Ingredient 2 is to consider for each of those scalar fields one of these so-called non-minimal couplings, which shows up in the effective action of this form. It couples directly to the Ricci scalar for the space-time. That's not really a choice. These couplings are induced at one loop order, even if we by hand try to set this coupling constant to be 0 at tree level. These things are a generic feature of interacting scalar fields in any curved spacetime. That's been known for more than 50 years. And so the second ingredient that my colleagues and I have been including are these nominal couplings for each of these scalar fields in our models. I should also add, as you can see in the text here, the beta function, these dimensionless couplings C, generically run or rise with higher energy. So at inflationary scales, there's no reason to think these couplings should be arbitrarily small. They could be order 10, they could be larger. And so that's the second ingredient that we consider. So we go to sort of consider model building. We start with what's typically called the Jordan frame, where we include these non-minimal couplings explicitly. This is some function typically shown in this form. Here's this form you'd get from, say, these loop corrections. So we tend to have these quadratic corrections here, coupling directly to the space-time Ricci scalar. We have multiple scalar fields here, and we have some interaction potential. We can then perform what's called a conformal transformation, which might be familiar to you. What we're doing is stretching our map. We're not changing our coordinates. We haven't changed the space-time coordinates x. We've changed our map between points x1 and x2 in our 4D or 3+1 space. So we're stretching our space-time metric. And we do that all the time when we use a Mercator projection. That sounds very exotic. We do that all the time, actually. So this has many convenient features. And by changing our map, we can then bring our effective action into what's called the Einstein frame. It's called that because now the gravitational degrees of freedom take the familiar, extremely well-studied canonical Einstein-Hilbert form. So we've taken some unusual gravitational features here, mapped those into familiar gravitational terms, but we can't do that for free. We basically moved the somewhat unusual features from the gravitational sector. What we've done is induced, really, it's kind of cool. We've induced a curved field space manifold for the many interacting fields. That shows up at these non-canonical kinetic terms. That's unavoidable. We showed that some years ago. We also wind up stretching the effective potential. So the potential in the Einstein frame is stretched by that conformal factor as well. What does that do for the dynamics during and after inflation? We can consider a very simple, really kind of a toy model in the Jordan frame. Let's say we have two interacting scalar fields. They each have some self-coupling, some quartic self-coupling. We put in some simple way that they can talk directly to each other, some phi squared, chi squared coupling. We can consider more complicated models. This one's already has enough features to start with. If we plot this potential in the original Jordan frame with respect to phi and chi, it's going to look like a bowl. It's a pretty straightforward form. Once we've performed that conformal transformation, then the effective potential in the Einstein frame is stretched and becomes lumpy. We now have to incorporate this conformal factor. These non-minimal couplings need not be equal to each other. The self-couplings need not be equal to each other. We're going to find these hills and valleys. What I've done on this last slide is take this exact same quantity, but now plot it in polar coordinates for that in the field space. So instead of using phi and chi, I'm going to use r as the radius in field space, and theta is my angle within field space. And then you start seeing this really quite simplifying structure. These models generically develop local maxima and local minima. So what happens is you get this very strong single field attractor behavior. The fields generically fall off some ridge. If the initial conditions started anywhere up one of these hills, then you have an initial transient. It falls either into this side or that side. It finds some local minimum. And then it rides the rest of the way toward the global minimum with basically no turning in field space at all. That's a generic feature of these kinds of models. And what I was able to show in the more recent work with my colleagues is that single field attractor, the lack of turning in field space, that persists even for this first phase of reheating, the so-called preheating phase as well. Why do we like these kinds of models? These are among the best fit models for the CMB constraints around, and they fit them with almost no flexibility in terms of coupling constants or initial conditions. The strong attractor dynamics during inflation yields these very robust predictions for things like the CMB observables that happen to sit exactly in the sweet spot of, say, the Planck WMAP and other kinds of observations. So these are features that we like already. They're generic. They include features that we think are important to consider for high-energy model building, multiple interacting fields, each with a non-minimal coupling. During inflation, it leads to these really robust predictions for the CMB spectra, which is really great. So now we took that family of models, my colleagues and I, to say, well, what happens immediately after inflation? Let's look at reheating in these systems. So now, because we have this complicated field space manifold, we have to be a little more careful in how we study the dynamics. We have to be doubly covariant, not just respecting the space-time symmetries of general relativity, but also a kind of field space reparameterization. So we have these covariant derivatives in field space as well as in ordinary space-time. So it's not actually that much more difficult than what we learn to do in ordinary GR all the time. So what I'm going to do is consider the coarse-grained or spatially homogeneous background fields, and then consider perturbations around them. That's my notation here is the script phi's for the background fields, and the capital index I is labeling field 1, field 2, field 3, how many fields you have in your model. The first thing to note is even at background order, you get a much richer oscillation spectrum for the background fields. The fact that we have these non-minimal couplings yields these non-canonical kinetic terms. That's what this script G is showing us. That's this field space manifold. And that's really telling us that there's basically some Christoffel symbols in here. There's a lot of stuff going on in how these background order fields, these spatially homogeneous fields, will oscillate around the global minimum at the end of inflation. So whereas if we just by hand turn off these couplings, we're going to have a series of peaks in our kind of fast Fourier transform. It's not just cosine omega t, you have some higher harmonics. You get a much richer harmonic structure, even with a rather modest value of these non-minimal couplings. That matters because it's this harmonic structure that's directly tied to the resonant structure of the fluctuations, where you're going to get these exponential instabilities. This is part one. I'm going to plant the idea of where I think it'll be really hard, but hopefully pretty interesting to see if there's a way to emulate some of these effects in some of these beautiful experiments that your group has been doing. What can we do about the kind of richer harmonic structure that I think is, again, a fairly generic feature of these models that have these other features from high energy physics? We can then move on to look at the behavior of the fluctuations. And so now, again, we want to be a little more careful to use this kind of doubly covariant formalism, both for space-time and for in the field space. And so again, I've introduced these Mukhanov-Sasaki variables. These are gauge invariant to linear order. As a reminder, these are a linear combination of these field fluctuations, which themselves are gauge dependent, and a gauge dependent metric perturbation, but that combination is gauge invariant, at least again, to first order in fluctuations. Then you again get actually not such a horrible looking equation of motion. You can stare at it for a while. It's the form you might expect from, corrections to the geodesic equation in the face of external potential, even for ordinary GR. So it has the features you might expect. This mass matrix is really pretty juicy. It involves three distinct kinds of contributions. So if we had just ignored any of these nominal couplings, if we had just gone ahead and ignored the fact we want to use gauge invariant parameters, we might have simply said, well, the mass is determined by the second derivative of potential. How else do we determine the mass if we have some interaction potential V of phi and chi? Those contributions, of course, are important. But we also have contributions from the fact that we have this induced field space manifold. These non-canonical kinetic terms show up in the evolution of the fluctuations. That's proportional down to the Riemann tensor of the field space. And even separate from that, we have the contributions from the coupling to gravity. That the fact that these are perturbations that are in some sense mixing fields and metric perturbations induces a scalar gravitational component to the behavior as well. So we have to track all three of these contributions, and they don't all obey a strict hierarchy. They depend on the model, they depend on parameter space, and so on. So we can consider the kind of diagonal contributions. Let's say, what's the effective mass for, say, the fluctuations of field 1, which I'll call phi? What's the effective mass for the fluctuations of field 2, which I'll call chi? Generically, it'll have these three different kinds of contributions. But again, if you stare at these expressions a bit longer, you can see in these single field attractors to background order, the chi field tends to be quiescent. Chi vanishes, chi dot essentially vanishes. And so the Riemann term here vanishes from symmetry. It could only get contributions from phi, and R phi vanishes identically. So there's no contribution to this mass term from this very otherwise interesting term. Meanwhile, if the chi field is quiescent, then the chi fluctuations get no contribution from this term that comes from coupling to gravitational degrees. So even for a very symmetric looking interaction potential, they both had similar self-interaction terms. There's a kind of symmetric direct coupling. You can have very different effective masses, very different effective frequencies for the fluctuations because the mass depends on more than just the potential. Okay, and that's where some terms could literally vanish, others could dominate. So here's some quick examples for the phi fluctuations and the chi fluctuations as we vary the strength of those nominal couplings. You can see that, again, this is now numerically solving the effective mass. The red is the combination, the actual full effective mass squared. And what we're showing is the blue are the contributions from basically second derivative of the potential. The gold are these terms from these non-canonical kinetic terms. And the green is from the coupling to the gravitational degrees of freedom. And you can see that gravitational degrees of freedom, as they should, play no role whatsoever numerically for the isocurvature modes, the chi fluctuations. Meanwhile, the non-canonical kinetic terms, the fact that we have this Riemann tensor of the field space, that plays no role in the evolution of the adiabatic perturbations. And as we tune up the nominal coupling, you can see some really dramatic differences in the effective mass, or essentially the effective frequency, for these two different types of perturbations. Remember, I said earlier, we expect large amounts of particle production when this adiabatic parameter strongly exceeds 1. And the more spiky, the more sharply peaked these effective mass becomes, the more likely you are to dramatically violate this adiabatic condition. So here's an example where you have a very strong hierarchy between pumping energy into the isocurvature modes rather than adiabatic. Even for this intermediate coupling case, you see the fact that you have these different contributions to the effective frequency can yield very different outcomes for where you dump most of the energy density when you evacuate the energy that have been driving inflation. So that's as far as we can drive from studying the field equations to linear order and perturbations. I think it's quite remarkable we found non-perturbative effects even at linear order. That rarely happens. But we're not done. And that's what I just much more briefly talk about some of the more inherently nonlinear processes as well. So as I mentioned just a moment ago, preheating, that early phase, that resonant phase, is non-perturbative, even though it's linear. We rarely see that in physics. It's the effects are not kind of a power series and some small coupling constant, even though we worked only to linear order in perturbations. Nonetheless, we really do need to go further to study kind of higher order moments in, say, delta phi, delta chi, and so on. These fluctuations themselves can begin to interact with each other. So to study that, I began working with my friend Tom Giblin and a great set of collaborators. 10 or so years ago, Tom and some of his then students had produced a very lovely lattice code. You can see his URL here, called GABE. That stands for Grid and Bubble Evolver, and you can read more about it here. This works by evolving coupled fields. You can put in basically any interaction potential you'd like on a self-consistent expanding FRW background, but it's unperturbed. So the original version of GABE does not consider metric perturbations. And I won't linger on this, just say we did the usual kind of lattice things. We vary the UV cutoff, vary the number of points and box size, and we find good numerical convergence. This is a well-controlled lattice environment in which to study things like these nonlinear processes. So now we want to study these same family of models on the lattice. And instead of making this sort of by hand separation, as we did for the linear analysis between kind of background fields and fluctuations, we're just going to study these fields, and they have a value at each moment in time at each lattice site. So these fields, phi 1 and phi 2, or phi and chi. So now we can get an approximation of these homogeneous background fields by taking a lattice average, an ensemble average at one moment in time. That gives you something like this sort of script phi. And likewise, we can track the RMS fluctuations, kind of lattice point by lattice point, and that takes the role of these linearized fluctuations, though here we're no longer limited to a linearized analysis. For the models that we've been considering, we have 2 scalar fields and 5 parameters. So what we did is try to figure out what's a useful way to study the evolution of these perturbations across different families of models, different types of parameters, and then as we vary the parameters numerically themselves. So not all the parameters are actually independent. It turns out in these single field attractor models, the amplitude of the CMB perturbations, the things that we really want to get right on the CMB sky, those are controlled by this combination of this quartic self-coupling of the dominant field, the field in which the system is evolving, I'll call that phi, and that same field's non-minimal coupling. So these two are fixed by observations. You have to fix that ratio so you don't wildly distort the CMB. So that is one way we impose that by hand to cut down the number of independent knobs to turn. And then we varied the coupling C for the phi field over 2 orders of magnitude. And then we just developed these kind of families. Say, what if all the couplings are identical symmetric, if there's some sort of gauge symmetry that enforces some symmetry among the couplings? And then what if one field's couplings are a bit larger here than the other? What if we have a so-called negative ellipticity or positive? It depends on which of the nominal couplings is larger. We just want to get a kind of controllable handle to study different kinds of effects from this family of models. And then we began using this beautiful program, GABE, to study distinct types of nonlinear processes that emerge when we throw the whole thing on the lattice. So in the blue here is the inflaton condensate. That's that phi field lattice average. That's like script phi. That's now time average, so its amplitude is falling as the universe expands. This is now E-folds after the end of inflation. And so the first thing we can ask about is, when does that become comparable in amplitude to the background, to the fluctuations in the fields when they start getting pumped and go into these exponential instabilities? So when does the background no longer dominate many orders of magnitude compared to the energy density and fluctuations? And that's the first time scale you can check, where here the black curves are the RMS fluctuations in the chi field, red is the RMS in the phi field, and the green is the linearized. If we just continued in our linearized form as we've done in the earlier studies, where there's no crosstalk between the different flavors of fluctuations, then the phi perturbations would simply just kind of, in this case, continue to redshift away. So we can compare with the linearized analysis as well. So the first question is, when does back reactions start to actually change the evolution of the background fields? And that's when you see the blue solid curve departing from the dashed curve here. As we tune up the strength of nominal coupling, you see quite a dramatic departure. So that sets a time scale for when you have to worry about a certain kind of nonlinear process. There's a different time scale. When does the amplitude of the fluctuations in the chi field become comparable to the background field? And likewise, when does the phi field begin to grow, not because of a resonance from the preheating phase, but now because of rescattering, because of inherently nonlinear processes, because essentially chi particles are kicking phi particles and raising the amplitude of those fluctuations. That's a distinct time scale. And that all changes as we change the value of this nominal coupling. Likewise, we can ask more coarse-grained questions more relevant immediately for the cosmological evolution. When do we get the energy out of the background field? We have to get the energy out of that inflaton field and into created higher momentum particles. What's a time scale in which the energy density in background becomes comparable to energy density in fluctuations? And likewise, again, distinct physical process, when does the universe achieve a radiation-dominated equation of state? Is it 1 E-fold? Is it 20 E-folds? That depends on how we map things like CMB predictions. And so this is just combining this, as you vary now the strength of the nominal coupling, you can see they kind of track each other as you tune up the strength of the nominal coupling. Most of these different measures of nonlinearity track each other. And you see that within, say, 1 to 3 or 3.5 E-folds, you tend to see each of these distinct nonlinear features sort of get achieved. And so to summarize, and we did the same thing across the other kind of sets of parameters where you have positive ellipticity, negative ellipticity is one self-coupling larger than the other, and so on. The pattern is actually quite robust. We wrote the longer article to do that more thorough parameter space search. That within about 3 or 3.5 E-folds, independent of which the microstructure of which parameters are larger than others, you get this highly efficient achievement of each of these kind of quintessential nonlinear features. I haven't yet talked about the equilibrium state. This is the last main thing I want to mention. Preheating, that early burst of highly resonant transfer of energy, produces a highly non-thermal distribution. You have growth only in certain bands of wave number or momentum k. You get nothing like a thermal spectrum. So what's the time scale during which the energy density you've pumped into fluctuations relaxes by things like rescattering into something that's going to approximate an actual thermal spectrum from which one could infer an actual equilibrium temperature? And so this is now showing that happening again in one instantiation of these models, where the coding's a little complicated. But basically, you watch time flowing upwards. So the blue curves at the earliest moment, roughly 2 E-folds after this process started, then orange, then green, then black. So by the end, you're seeing something emerge that looks like the kind of smoothed out, essentially Maxwell-Boltzmann-like distribution from which you could try to infer, in this case, a kind of classical temperature. Of course, these are classical lattice simulations. But that depends, you only get there because of these inherently nonlinear transfers of power from two particles with one momentum scattering into a different momentum state and so on. So let me wrap up. I hope I've convinced you that we really should continue to study reheating. This is essential to map these otherwise glorious successes of our understanding of cosmic history, and also to set up the great successes of the standard Big Bang model. We need a universe that at some early time had a radiation-dominant equation of state, standard model particles, and in equilibrium at high temperature. If we don't have that during inflation, how do we get there? So that's one good set of motivations, I think, for continuing to study this phase. And you can get pretty far into that in this linearized approximation, so-called preheating phase, but not all the way. And so we really do have to be looking at these inherently nonlinear processes, which have distinct timescales. And these models that I've suggested include what I would consider realistic features for energy theory. They tend to be actually quite efficient, even for not enormous values of these non-minimal couplings, they tend to achieve each of these criteria within a handful, 1 to 3 E-folds. And so that leaves many more questions to ask. Can we more thoroughly incorporate gravitational degrees of freedom in these lattice simulations? Can we incorporate higher spin decay products in these lattice fields? How can we understand thermalization more physically? And here I'm going to turn it back to all of you. What clues can we get to these kinds of physics questions from doing exactly the kinds of really lovely experiments that your group's already been immersed in? Thank you.
Thank you very much, David.